Hi, everybody. Continuing on in our treatment of improper integrals, last time we finished up with the example of Gabriel's horn. Now I want to take up a little bit different topic. What if your definite integral is improper at both ends? Like, what if you need the signed area underneath f of x over the entire real line from minus infinity to infinity? So you're improper at the left-hand endpoint and improper at the right-hand endpoint. What should you do? The books define such an integral as the improper integral from minus infinity to 0 of f of x plus the improper integral from 0 to infinity of f of x dx. It actually doesn't matter where you break it up. You could break it up into 0 or negative 3.2 or 5.8. Doesn't matter. But break it up into two pieces, and you'd get the same results anytime. So let's go ahead and try this out on the area underneath the curve y equals 1 over 1 plus x squared. So this is defined for all real numbers x, and it kind of looks like that. It's the biggest at x equals 0, it becomes 1. And it heads towards the x-axis in either direction. Is the area underneath that finite? If so, what is it? So first we'll handle the integral from 0 to infinity of 1 over 1 plus x squared. But before I do that, let me get my coffee on. All right. So we're looking at the integral from 0 to r, 1 over 1 plus x squared. But hey, the antiderivative of 1 over 1 plus x squared is inverse tangent. So evaluate that between r and 0, and we're looking at the limit of that expression. Now, inverse tangent is the angle whose tangent is the given number. And the way they define inverse tangent in most textbooks and in our textbook is that the angles for the given values have to be between minus pi over 2 and pi over 2. You know, with any inverse trig function, there's infinitely many angles that would have a given like tangent, but they only pick out for the inverse trig function those angles between minus pi over 2 and pi over 2. So if you're asking for an angle whose tangent is 0, you're going to have to pick 0 radians. So that expression is going to be 0. So we're left just with this expression. The limit as r goes to infinity of the inverse tangent of r. And so we're wondering, like, what angles between minus pi over 2 and pi over 2 would have really big tangents, because the r is getting to be a really big positive number. So there's a couple of ways to think about this. One is you could just go and look at a graph of inverse tangent. So like I went to Wolfram Alpha and asked for a graph of y equals arctangent of x, inverse tangent of x. And it gave me a couple of views. I'll use this bottom view here where the x ranges from minus 12 to 12. And along the y-axis, you get your angles, and you'll notice that like it seems to go up to a level, looks like about a pi over 2, and down to a level that looks like about pi over 2. And if you wanted the limit as x goes to plus infinity, you're heading up to pi over 2. If you want the limit as x goes to minus infinity, it looks like you're heading down to minus pi over 2. So you could figure limits out like that by looking at a graph. I think it's also extremely useful, though, to kind of get down to first principles and think of it in terms of unit circle trigonometry. So I'm going to just adopt this approach here to give you some insight into this. So I'm looking for this limit. And so I'm wondering, like, what angles between minus pi over 2 and pi over 2 would deliver me really big positive tangents, r going to plus infinity. So I think of my unit circle, and I think about angles between pi over 2 and minus pi over 2. So, pi over 2 would be the 90 degrees. Minus pi over 2 would be down this way along the y-axis. So I'm thinking here of an angle theta that's pretty close to pi over 2. It's a little less than pi over 2. By definition, the coordinates of the point where this ray from theta intersects the unit circle are cosine of theta and sine of theta. That's just the definition of cosine and sine in unit circle trig. So when our theta is just a bit less than pi over 2, then you can see the sine of theta, the y-coordinate, is going to be pretty near 1. The cosine of theta, the x-coordinate, is going to be a small positive number, okay? And so the tangent of that angle theta you're looking at there, sine over cosine, would be about 1 divided by small positive makes a big positive number. So this verifies angles just below pi over 2, they deliver the really big positive tangents. Another way of saying it is that the limit of tangent of theta as theta goes to pi over 2 from the minus side is infinity. And so if you're looking for the limit of angles whose tangent is bigger and bigger numbers, you would have to say that's pi over 2. Okay, well, that expression was what the improper integral reduced to. So now we have found one of the improper integrals. That area from 0 to infinity underneath the curve is pi over 2. Now we need to get the other area from minus infinity to 0 underneath the curve. Now this curve, 1 over 1 plus x squared, is symmetric around the y-axis. For any value x, it gives the same height as it would give at the opposite of that x, because the square of a negative is positive. So the area that you're looking at there ought to be pi over 2 as well. But let's go ahead and check with the improper integral as a way of continuing to practice our thinking. So integral from minus infinity to 0. Limit r goes to minus infinity, integral from 0 to r. Use fundamental theorem of calculus. Antiderivative is still tangent of x, but evaluate between r and 0 now. So tangent inverse of 0 minus tangent inverse r. Tangent inverse of 0 is still 0. I've got minus tangent inverse r, got to take its limit. That's minus the limit of tangent inverse r as r goes to minus infinity. So now when I think about the unit circle, I want to look for angles between minus pi over 2 and pi over 2 that deliver big negative tangents. And those would be angles that are pretty close down to the minus pi over 2. So this angle from the positive x-axis here down to this ray that I'm showing you, that's a negative angle pretty close to negative pi over 2. And as you can see, when I think about its sine of theta over cosine of theta, sine of theta is the y-coordinate. It's pretty close to minus 1 this time. It's approximately minus 1. The cosine of theta this time, the x-coordinate, is still a small positive number. Minus 1 over a small positive makes a big negative. So sure enough, if you're looking for big negative tangents, you've got to be looking at angles that are close to minus pi over 2. And so as r goes to minus infinity, tangent inverse of r is headed to minus pi over 2. Now, we were looking for minus that limit. And so our improper integral is minus that limit. It's plus pi over 2. So we got pi over 2 on both sides. The total area underneath the curve is 2 pi over 2's. That's pi. Let's try another example. This is just a regular improper integral that's improper in one direction, plus infinity at the top. But I just want to show you what might happen if you have to use integration by parts to get your antiderivative. So when I'm looking for this antiderivative, a natural choice, because it's a product here, is to try integration by parts. Let u be x, dv is e to the negative x dx. It's everything else. V is easy to get. It's minus e to the minus x. And du would be just dx. So I use the integration by parts, and I end up having to work with the antiderivative of e to the negative x, which is minus e to the negative x. So the full family would be the uv minus the integral v du plus a c. Of course, I only need one member of that family to work with, one antiderivative, when I'm going to use the fundamental theorem of calculus. So I'll just pick on that one. And so my improper integral would be the limit r goes to infinity of the antiderivative I've picked out, evaluate between 0 and r. So plug in r, subtract off what I get by plugging in 0. E to the minus 0 is e to the 0, which is a 1. I simplify a little bit, and I kind of stare at this and wonder, what's it going to as r goes to infinity? And so 1 just stays at 1, okay? Now, e to the minus r, that gets very small as r gets bigger and bigger, so it goes to 0. But what about this one, r times e to the minus r? There's kind of a war here. R is getting big, e to the minus r is getting small. What does that make the product? Well, I can use L'Hopital's rule on that little problem. So thinking about what I got here, I've definitely got the 1. And I'm going to have this minus sign from here. And now I'm just going to focus in on getting that limit of this. Now I'm going to write the e to the minus r as 1 over e to the r. So I've got this limit I'm working on. And I notice now I've got a numerator that's headed to infinity and a denominator that's headed to infinity. I've got an infinity over infinity indeterminate form. I could use L'Hopital's rule on that. L'Hopital's rule says that the limit of that form will be the limit of the derivative at the top over the derivative at the bottom. With respect to r, since that's the variable here, derivative of r would be 1, and derivative of e to the r would still be e to the r. Look for that limit as r goes to infinity. That's a 0. And so the whole thing is just 1 minus that limit. 1 minus 0 is 1. That would be the area underneath this x times e to the negative x curve that graphs something like that. Okay. Another situation, but let me get my coffee first. What's this shaded area that I'm showing you here? So it lies underneath the curve y is 1 over the square root of x. And it's over the x values from 0 to 9. And the y-axis is helping to bound it from the left, just as the line x equals 9 is bounding it from the right. And so you'll see there's something improper about this situation. You know, the function here, the the 1 over root x, is unbounded as x gets closer to 0. It gets higher and higher and higher. It has y as a vertical. It has the y-axis as a vertical asymptote. And so there's like an infinite length of skinnier and skinnier area going up, 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 up along the y-axis, and you wonder, is the total area finite or what? So if you thought about it as a definite integral, it looks like integral from 0 to 9, 1 over root x dx. Both the limits are just finite real numbers, but the impropriety of the integral, what makes the book call this an improper integral, is that the function is unbounded as you approach one of those limits. So that is a second type of improper integral that we learn to treat in this section. The idea for treating it is very similar. You sneak up on what's improper. What's improper here is this bound of 0. Look at the area underneath 1 over square root of x, not from 0 to 9, but from r to 9, where r is some number that's a little bigger than 0. That shaded area you could find the regular way, and now you just got to move the r closer and closer to 0. R will be positive, but you move it closer down to 0, and you take the limit of the areas you get. So the formal definition of this type of improper integral is, if you've got some function, f of x, that gets unbounded, either plus infinity or minus infinity, as you come to some number a, then if you want the integral from a to b, then just take the limit as r goes to a from the plus side of the integral from r to b. Similarly, if the impropriety had been at b, you would take the integral from a to r as r goes to b from the minus side. You would creep up on it in the same way. Well, let's try out our example. So this comes to this. Now I'm going to write 1 over square root of x as x to the negative a half, because I'm going to be able to get the antiderivative easily with the power rule. So it would be x to the plus half over 1/2. Okay. So actually, there's a typo here. There should be no negative sign here. There therefore should be no negatives here and no negative here. So I'm going to take those away when you see these notes. I'm going to evaluate between the 9 and the r, and so I have a 2 root 9 minus a 2 root r. And so I've got a 2 times 3 is the square root of 9, and I got a 2 times square root of r. Now got to let the r go to 0. So this part's going to go to 0, but this part's going to hang around at 6. And so the total area underneath that curve is a 6. I'll get rid of the typo here, here, and here right now so I don't forget. Hold on a minute. Alrighty. There's another general theorem related to this situation. This idea of, 1 over x to a power going from 0 to some positive number. So the impropriety here is at 0 because this is going to approach undefined, as x gets closer to 0. So if you were to work out such improper integrals, then it turns out that if that power is less than 1, there will be a finite amount of area underneath, given by that formula there. So like when our p was a half, it was a finite amount of area underneath. But there's infinite amount of area underneath if the p is bigger than or equal to 1. So it's kind of the opposite of the situation of the other p integral that went from the a to the infinity. Here's a useful idea when you have a really tough integral to deal with. Suppose that you've got two functions, f of x and g of x, and I've got them graphed here. And suppose that for all the x's bigger than or equal to some number a, so like here's an a on the x-axis, and suppose that the x is a bigger than or equal to a, and when x is bigger than or equal to a, suppose the f of x curve is above the g of x curve. So g of x is less than or equal to f of x. Suppose that happens. Also suppose the g of x is at least bigger than or equal to 0, like in the picture I have here, okay? It doesn't matter what happens before. It doesn't matter who's bigger or smaller before. But suppose that there's an a such that past a, the f is bigger than g, which is bigger than 0. Then, if the improper integral from a to infinity of f of x converges, then the improper integral from a to infinity of g of x converges. That should make sense. If there's a finite amount of area underneath the f curve, then there ought to be a finite amount of area underneath the g curve because the g curve is lower. Second fact, suppose the improper integral from a to infinity of g of x, and there should be a dx there, so I'll write it in. Dx should be like right here. Suppose that diverges. Then the improper integral from a to infinity of f of x would diverge as well. That should also make sense. If there's infinite amount of area underneath g, there should definitely be infinite amount of area underneath something that's higher than g. So that's the so-called comparison test for improper integrals. Why did they call it a test? Well, it's the way you can use it. For example, suppose you're wondering, Does this improper integral converge or diverge? Well, try as you like, it's going to be really, really hard to get an antiderivative for 1 over the square root of x cubed plus 1. And so applying the fundamental theorem of calculus and integrating from 1 to r, and then taking the limit as r goes to infinity, that's going to be a lot of work. So instead, think like this. You know, sure wish I could just see an x cubed instead of an x cubed plus 1 there. That would be a lot simpler. And you know what? X cubed plus 1 that I have is bigger than x cubed. And so the square root that I'm looking at in my problem is bigger than the square root of x cubed. So my integrand, the reciprocal of that square root, would have to be less than the reciprocal of the square root of x cubed. You know, when a number is bigger than a number, the reciprocals are the other way around. 3 is bigger than 2, but 1/3 is less than a half. So I've got, for all x's that I care about, all x's bigger than or equal to the 1, that's my lower limit here, I've got a hard and fast argument that my function, my integrand, is less than this function. So let me see what happens to that other function from 1 to infinity. Well, whoa, that's one of those p integrals. The p integrals from the a to the infinity, like in that theorem 1 that we did earlier in the notes. And we learned that when the p power was bigger than 1, the integral would converge to some finite number. So this converges to some finite number. So this one is also going to have to converge to a finite number by comparison. Basically, this is the f in the comparison test, and the integral that we started with was the g. So I don't know what finite area this converges to, but I know that it has to be a finite area. I want to leave you with a little caution. Say that you're looking at this definite integral wondering how to evaluate it. And you think, you know what? I don't see any infinity here. I don't see any infinity here. It looks proper. And, you know, let me check for unbounded. When x is 2, this is just a 1 to the 2/3, just a 1 to the 2/3 is a 1. 1 over 1 is 1. You know, this is a totally defined number. And when x is 0, it's a -1 to the 2/3. -1 squared, 1. Cube root is still a 1. 1 over 1 is a 1. So I'm not like unbounded as I go to the 0, and I'm not unbounded as I go to the 2. Looks like I got a totally proper integral here. Well, you actually don't. The thing is that this function is undefined when x equals 1, and 1 is in between 0 and 2. In fact, if you did the graph of 1 over x minus 1 to the 2/3, you would see something like this. The function has vertical asymptotes at the vertical line x equal 1. And so when you're asking for the area underneath, you're asking for this area and like all the way up along this side of the line x equal 1, and this other area, including like this, all this stuff up along the other side of x equal 1. Is that a finite amount of area or not? If you want to deal with that, you're going to have to break the integral up at the place of discontinuity, at the 1. So do the integral from 0 to 1 and the integral from 1 to 2, okay? The integral from 0 to 1 is an improper integral because the function is unbounded as you get to 1. The integral from 1 to 2 is improper because the function is unbounded as you get to the 1. And so you'll have to set up these two improper integrals. The first one here, you go 0 to r and let the r approach 1 from the minus side. And the second one, you're going to go from r to 2, and you're going to let r approach 1 from the plus side. And so you have those two separate limit problems that you have to work out. If you want to see the details of how to work them out, this example is actually in the textbook, and so you can look up how it ends. That's all I've got for now. I'll see you later.